This is the second example I hope to cover on the new topic of differential calculus to achieve optimization. And in this question here, instead of finding the minimum of something, we're going to try and maximize volume. So let's just begin the question and see what's happening. So an open trough as shown, so this is like a trough shape, triangular prism. We have x and x here for the sides of the triangle, and h seems to be running along what would be the length. So, and it has a surface area of 4 meters squared, so all the surfaces combined have a total area of 4 meters squared. So this information will be useful later. So it's really important that when we read the question we understand what may be important. So part A, show that h has the expression 2 over x, take away x over 2. So it looks like we're going to have to use the information given for surface area and some geometry knowledge for triangles and rectangles to achieve this. So let's begin with part A. So solely dealing on surface area, we know that the surfaces here, we have a triangle and we have another triangle, rectangle and rectangle. So really what we're doing is the area should be the front, back, plus the sides. The front and back being the triangles and the sides being the rectangles. So just remind yourself of the formula for area for a triangle and a rectangle. Triangle is a half times height times base. So in this case for this triangle, a half times the height, which is x, times the base, which is x, so a half times x times x. And for the rectangle parts, we'll have x times h, and we'll have 2 of those. So putting some numbers in, we've got A, which we were told the surface area in total was 4 meters squared, so that goes in place of A. The front and the back areas, 2 triangles, a half times x, and we've got 2 of those. And we have 2 of the rectangles, in this case they've got the algebraic expression of x times h. When we simplify this, we can see that we've got 4 equals x squared, so the half cancels out the 2, and that leaves us with x squared, and that's the triangles dealt with. Now the rectangles, we've got 2 of these, so x times h, just x, h. 2 of them, and it looks like that. So this is an expression for the surface area, however, it contains h. So we'll start rearranging and trying to isolate h and then hopefully achieve the expression in h in terms of x that question A had shown us. So taking away x squared from both sides, 4 take away x squared, and then we have another problem to deal with now because we have 2x times h. So dividing both sides by 2x in this case. Now with some simplification we should arrive at the show that version of h we've seen earlier here. So 4 and 2, they will cancel out numerically, and that will give us a 2 on the top with 1x, so 2 over x. And then we've got x squared all over 2x, so again x's will cancel out, so we have no x any longer on the bottom, 1x only on the top. And this gives this. If we've achieved to show that, I usually write as required because that reinforces the idea that you've arrived where you need to be and you've achieved to show that was set out earlier in the question. So 2 over x take away x over 2 equals h. So part A is now complete. Show that the volume of the trough is given by this expression now. So again, this is the first time we're talking about volume. And again, just remind ourselves of the volume of this trough. So this looks like it used to be a cuboid and then we've cut it in half. So a cuboid has a volume of length times breadth times height. In this case we'll just put a half in front of that and we've achieved what would be half a cuboid, in other words this trough, the volume of this trough. Anyway, let's start at part B. So volume is equal to a half times the usual cuboid because we've got a triangular prism which is now half of the cuboid. Let's substitute some of the information in. So we don't know volume, so that stays as V. We do know the length of the trough, which went along for h. We know the base is x, and we know the breadth is also x. So when we simplify this and combine it, we'll end up with a half hx squared as an expression. However, if we go back up to part B, this expression for volume contains only x's and doesn't have an h. So like the previous example, we are going to have to substitute h in terms of x squared, or in terms of x. So from part A we had h is equal to 2 over x, take away that, so what we're going to do is substitute this into this expression here in place of the h, like so. And with a bit of multiplication, multiply out by a half. First you'll see that 2's cancel out, then we'll have a quarter on the second expression. Remember how you multiply out fractions, multiply 2 tops, 2 bottoms. So the first expression here, without the x squared, will be 2 over 2x, take away x over 4. And we still have to multiply each of these terms by the x squared, which will lead to some cancelling and changes in the powers. V is equal to, so that's me cancelling down, 1 over x, x over 4. Should just put 4 like that. And x squared over x, take away x cubed over 4. And when we cancel out our x's here, we arrive at this. And again, going back to part B, that's exactly as we require. So part B, we have now got the expression for volume. We have achieved that. We haven't done any differentiation yet. That will come now in part C. Show that the minimum volume x, for the x value that causes minimum volume, will be 2 over root 3. So let's have a go at part C. So volume was given in part B, and I've written it now in function notation with the x here. So volume is a function of x, and the function that we process is x, take away a quarter x cubed. So differentiate that, because that's ready to be differentiated as it stands. So x, remember 1's on that power, and then power of 0, which is just 1. So 1, take away 3 over 4. We had a quarter times by 3, 3 over 4, 3 quarters, x squared. Write the statement about what happens at stationary points, because we're interested in these stationary points, because they might give us ideas for maximization, minimization, in this case hopefully maximization, because we're trying to maximize the volume. Equate this derivative that we got here to 0 and try and solve for x that will achieve the value of x at those stationary points. So rearranging, we have this, timesing both sides by 4, dividing both sides by 3, and now we've got an x squared term equals 4 over 3. So in this case we're going to numerically have two values here because of a positive and negative square root. And the only thing we can do with this 4 over 3 fraction in the square root is we can find the square root of 4, which is 2, so we'll end up with 2 over root 3. This is now looking similar to the number that we already seen in part C here. And it looks like the positive version of our square root is in fact the value for x, which maximizes volume. We can verify this through an extra table, and in this case we need two extra tables. We're going to take the negative version here of 2 over root 3, go slightly to the left and to the right, so we get an idea of what's happening on both sides. Do your substitutions here as usual. Every time you substitute in the particular value for x that you solve for here, it will always give you a gradient of 0, because that's this statement here. Either side of that stationary point, we've got a negative value, which causes a negative gradient. We've got a positive value, which causes a positive gradient. So here we've got a minimum turning point at x equal to negative 2 over root 3. Now we do an extra table for the positive version of the point next we have stationary points, which is 2 over root 3. And again, here we can just recycle our values here because each of the x terms are squared, which will not have an effect. So process 1 through the derivative gives us a quarter, station point gives 0, and substituting in 2 gives us negative 2. So in this case we've got positive gradient, flat line, negative gradient, so in this case we've got a maximum turning point. So there is verification that the maximization of volume occurs whenever x is equal to 2 over root 3. And if you want, you can put meters on the end of that, because that can now have a unit value because we're dealing in meters. So all we have to do now is write a statement. Volume is maximized at x is equal to 2 over root 3 meters, verified through the next row table calculations. And that concludes this example. Again, feel free to look through the working, pausing where appropriate. A lot of work involved in these questions, lots of marks obviously as well. And I hope that you understand that.